magnet from the prior page are circular, meaning the magnetic field in a bar magnet passes through the center of the bar magnet and comes out of the bar magnet. It goes back through. It forms a circular path through the object, which is why when you break a bar magnet up into pieces, you can't break off a north end and a south end of a bar magnet. If you break the bar magnet into pieces, you get a new north side and a new south side. You don't break away the north end of the magnet and the south end of the magnet. And I don't care whether you understand it or not, doesn't matter. This is what happens. There are no magnetic monopoles. There is no north pole that is a single point in a magnet. Again, where the magnetic field comes from inside a bar magnet is not obvious. And that's not the point of today's discussion. The point of today's discussion is to understand that the magnetic field is dynamic, it is circular, has no point of origin and no point of termination, and exists only because there is a movement of a charged particle. The moment I stop the movement of this particle, the magnetic field would disappear, it would go to zero. Now, charged particles didn't experience a magnetic force unless they were moving. That was the big takeaway from last week, that a single point charge in space could not be started into motion nor stopped by the action of a magnetic field. That a charged particle had to already be moving, and it moving through space in a region with the magnetic field caused a force on the charged particle. So it shouldn't surprise you that a particle that sits still in space, although generates an electric field, does not generate a magnetic field. So remember, the electric field is going to still be there. I'm not going to be drawing in the electric field. I'm going to focus on the magnetic field today, okay? Now, the moment we give that particle a velocity, however we choose to do so, the moment that particle has a velocity, it begins to immediately produce a magnetic field. Now, that magnetic field is a little bit interesting in that the magnetic field produced by a moving charged particle is circular. It's circular. And to understand the direction of this circle, it's a right-hand rule procedure. It's the curl rule. And if you were to point your thumb in the direction of the velocity, your fingers will curl in the direction of the magnetic field created by the moving charged particle. So, thumb this way, I have a circular field, and to try and put a clearer understanding about that, that circular field is out of the board on top of the particle and into the board below the particle. So it's a circle though. So if I were to draw this particle with a velocity coming straight at us, so this is the same charge, but coming straight at us, the magnetic field would be circular in that direction as it approaches us. Again, right-hand rule, velocity out of the board, magnetic field is wrapping around it in a counterclockwise direction from the board towards you. There's a lot to unpack here that's not obvious, and I want to draw your attention to it. First, in the first picture, you'll notice how I made the circles smaller, and they got bigger, and then smaller again. This magnetic field is got a distance component related to it. So if I was located, say, here at point P, as this particle passes me, I would detect a magnetic field that was increasing in strength and then decreasing in strength as it passed me. So the size of this magnetic field is proportional to how far away from the particle you are. But this isn't static. So it's hard to recognize the fact that it's producing a magnetic field that is tapering off the further away you are from the particle, but the particle is moving. So you're going to get this effect of the magnetic field increasing and decreasing as the particle passes by you. Now, we'll get to the mathematics of that in a bit. I think this is already quite a bit to unpack, but there's also something more important than I said. This is the most important thing I'm going to say when it comes to the structure of the magnetic field. Magnetic fields have no point of origin and no point of termination. Electric fields, say, originated at positive charges and terminated at negative charges. They had a clear point of origin and a clear point of termination. Magnetic fields do not. There's no origin or termination of a magnetic field. It is a perfect loop. All magnetic fields, even the ones, the law that's designed to help us understand the size of the magnetic force is no fun at all. It's Biot Savarte, and I have no idea of the history of the Biot Savarte law, why there's two names. I'm sure it's not the same person with a hyphen. I'm pretty sure it's two different people are credited with this work. And the work predates point charges. So I want you to understand that all of the work that went into the Biot Savarte law that we're going to see now was based on the flow of current, which we also know is the flow of positively charged particles in a wire. So what we have is a conglomeration of lots of testing that has kind of given us this law. We won't be using this law very much, and you'll be happy to know that we won't be using this law very much. But this law is supposed to be able to tell us the size of a magnetic field at some point in space where there might be moving charged particles. So this law is from the standpoint of point P. And it would tell us the magnetic field at point P. Please understand that this magnetic field assumes that the particle is at a certain location, but we know that particle is moving. So the Biot Savarte law can't tell us very much because the particle keeps changing position. You understand? Whatever we get through the Biot Savarte law, it's transient. So obviously, I think there's some things we're going to need here in using the Biot Savarte law. And the first one is we probably need a variable that relates how far away we are from where the particle is. And we traditionally use lowercase r for this. Again, please stop using the word radius here. This is just a distance from the moving charged particle to our location in space. The magnetic field produced by a single point charge is proportional, and it's proportional. I'm going to have to kind of move this over here because I need room. The Biot Savarte law is big. The Biot Savarte law is going to be proportional to several factors, and I think you kind of know what these factors probably are. Like, it probably has a distance component to it, like how far away we are from the particle. It probably has something to do with the size of the charge, and it probably has something to do with the speed at which the particle is moving. So I think it makes sense that all of those things would probably play a role in determining the size of the magnetic field. But of course, like anything else, there's a proportionality constant too. So I'll put the proportionality constant out front. And I'll fill that in just a minute. But the way that these things interact is a little bit bizarre. There's going to be the charge, Q. And then there's the velocity. And then there is separation distance. So the magnetic field has a similar proportionality restriction as we have for Coulomb's law and the electric field, that it is proportional to our distance away squared. Unfortunately, just like electric fields, magnetic fields are vectors. And the direction of the magnetic field is related to the direction of the velocity, but also related to where you are relative to the particle, making our next part a little less fun to write. You see, the direction of the magnetic field is related to the direction of the particle from you. But r is in the denominator of this relationship. Therefore, we put v cross r hat up here to say that the direction of the magnetic field is the cross product of the velocity and a single unit vector directed along r. This portion is to give direction to the magnetic field and only give direction to the magnetic field. R is a unit vector, so it doesn't change the size of this value. It just helps us with the right-hand rule and to give us how much of our angle is perpendicular to the velocity. So I know it's a lot to take in, but this is Biot Savarte law. There is a constant of proportionality. The constant of proportionality has a new constant called the permeability constant, and it has 4 pi embedded in it. Mu naught over 4 pi is the thing that's all over this particular calculation. In the same way that k was related to 1 over 4 pi epsilon naught, we find that in magnetic fields, it's mu naught over 4 pi. So these are similar constructs. The permittivity and the permeability constant pollen counts high today. These words are just kind of created. Permittivity, permeability, they're not anything that has to really, like there's no real difference in what these constants say. They mean the same thing. They're both trying to impress upon you the idea that this is how well an electric field or magnetic field can be established in a vacuum. So we say the permeability constant is how well a magnetic field can be established in a vacuum, and we say the permittivity constant is how well an electric field can be established in a vacuum. They have kind of some weird properties. Weirder still are the units of these properties. The big important difference here is that we have found that these two things are related, and they're related in a really weird way. And we're going to come back to that in a little while, probably a couple of weeks, but they're related by the speed of light, meaning they are both proportional to the speed of light and therefore proportional to each other. These two measurements are apparently directly related. The electric field and the magnetic field are not very different from each other. They appear to behave very different, but they're not. They must have lots of things that are related in common. Also, mu naught is known exactly, where the permittivity constant isn't. The permeability constant is an exact number. And we'll talk a little bit about what it's about in a little bit. But again, the permeability of free space. So remember how often we saw the permittivity constant all of first semester? So mu naught is the constant for magnetic fields. And we're going to see it a lot. All of our answers all are going to end up with a mu naught in them somewhere. And because you see it in the numerator of this fraction, you better believe whenever you're asked to calculate the magnetic field, you should expect a mu naught in the numerator. The 4 pi, on the other hand, just like the 4 pi with the in the permittivity constant, it tends to get canceled out by things. The circular nature of the magnetic field is probably evident in why 4 pi shows up here. But let me not digress too far and say that consider, please, the right-hand rule that's being suggested here. It needs to be in agreement with the curl rule. We know that here, we expect the magnetic field to become out of the board because that's what the curl rule would supply. But the three-finger rule should tell us that too. Remember, it is V cross R. So for V and R to be in the same direction, I have to have my thumb out of the board, which is why V cross R and why R is drawn in this way, from the particle to our location in space. But we apply it here, saying the magnetic field is out of the board at this location. I want you to see that, but in practice, it will always be easier to use the curl rule to determine direction of magnetic fields. And so I just use the curl rule. Point your thumb in the direction of the velocity, and your fingers curl in the direction of the magnetic field. But before you leave, cross product is going to always produce a sine of an angle all the time. So all calculations for the magnetic field from a point charge involve the sine of this angle, the angle between r hat and v, telling you that the magnetic field is max when the r is perpendicular to v. So when it's like right down there, that's where you're going to get the maximum magnetic field. All right. Not knowing exactly where I left off yesterday, I did want to at least make a few points about the permeability constant. It's 4 pi times 10 to the negative 7th Tesla meter per amp. An interesting unit to be sure, considering that it's always paired with a 4 pi, right? It seems bizarre, but we're going to have this 4 pi showing up as part of our function, but yet 4 pi is actually in the value. I told you that it was exact, and it is. It's exactly 4 pi, but we know that pi isn't exact. Pi is non-terminating. Put that next to the permittivity constant, and if you don't remember, 8.85 times 10 to the, do you guys remember?
Negative 19.
Negative ninth.
Oh.
K is 9 times 10 to the ninth. This is the inverse of that, so we get the negative ninth in there. And its units are a little bit more bizarre. It is it is coulombs squared per meter squared newtons there. It's the inverse of K's constant. That's a lot to kind of fathom what all is going on in there. But these two constants kind of rule all of E&M in ways that might not be all the way clear, but should be starting to be clear. We already know how important epsilon naught tends to be. Electric fields are completely determined by the size of this particular value. And so for the next few weeks, we're going to talk about how the permeability constant has a similar function for magnetic fields. We will not use Biot Savarte for a point charge. I bring it up because this is what's happening for a point charge, but there's no real way to talk about the size of the magnetic field due to the motion of a point charge. It's so transient. Meaning we can find the value for this magnetic field at only an instant, but then the next instant, the particle's no longer there. So if you're trying to, looking at this definition of Biot Savarte, if you look closely, think of QV cross B and how it changed for a current carrying wire and became IL cross B. Create magnetic fields, which is what we want to do. We want to try and control the magnetic field in the same way that we've been trying to control the size of electric fields and to store energy in those fields. Then we probably would like a way to be able to grab a hold of or control a magnetic field. And so if you want to control a magnetic field, and clearly moving charged particles seem to be associated with that, what's the best way to control moving charged particles? Then use a current. Clearly, a current-carrying wire would have a large number of moving charged particles. And you'd be fully able to control their motion because you can control where that wire is and the shape of that wire and how many charged particles are moving through that wire. So the best representation for Biot Savarte is one that's been formulated to deal with a current-carrying wire as opposed to a free moving charge. And the current carrying wire, so we need a wire that we can say is our current carrying wire. I want to make it something that's not of uniform size or uniform shape, but I want it to be more or less infinite in nature based on the size of our board. And I want to point out a place relative to the wire. And I want to consider a section of the wire. So I'm going to use this section of a long wire, a piece of it, a delta X of the wire, if you will. Let's say that the wire has a total current I passing through it. Biot Savarte states that there will be a magnetic field generated around the outside of this wire due to the fact that there is a positive flow of charges through the wire. So again, Biot Savarte is based on positive current flow, like everything else. We use positive current flow as our nature here. And the size of the magnetic field, I'm going to say just a piece of that magnetic field, because there's lots of pieces of our wire, is probably exactly what you would expect. Biot Savarte for a current carrying wire, U naught over 4 pi, of course. Instead of Q, we're going to have I. I is not a vector though, so we will have delta X taking its vector direction. And all of this divided by r squared for our magnetic field at point P away from a piece of our wire. Of course, to get the direction, we will have to cross this with a unit vector pointing in the direction of r. So again, we'd have to establish that there is indeed a unit vector that points from our piece of wire towards our place in space. And our unit vector interacts with the direction of x to establish an angle between the two for us to make this necessary right-hand rule pronouncement for the direction of the magnetic field. So if I'm using the right-hand rule correctly and I point R in the direction of the, towards my point P from my piece of wire, and I rotate my hand to point in the direction of X, I find that, I'm not sure I'm doing this carefully enough. I find that my magnetic field is into the board. Not sure I'm doing it right. R is this way. That's better. So R cross X. It's just into the board.
Wait, doesn't X go first?
Yeah, X goes first.
What's that?
Should point out.
Oh, X is first, R is second. Thank you, sorry.
Yeah, okay.
X is first, R is second. Oh, so much easier. I thought I was trying to draw it intentionally so I didn't have to contort when I was up here, and I got up here and screwed up anyways. All right, yeah, you're right. X first, rotate to the direction of R, out of the board. So the cross product is still here to tell us the direction of the magnetic field at point P. It's also here to tell us how much of the current is actually actively causing a magnetic field. This angle will be used as part of our cross product. Now, something I didn't indicate yesterday that I probably should have, but we got interrupted by the bell and having to go outside. And so if our wire is pointing directly at our point, it doesn't contribute to the magnetic field. We get maximum contribution to the magnetic field when the current is perpendicular to R. And remember, that also is suggesting that our magnetic field is circulating around the outside of the wire. We could use the other right-hand rule, in fact, to determine the direction of the magnetic field by just placing our thumb in the direction of the current and rotating our hand around the wire, acting like we're grabbing it, which would produce a magnetic field around the wire that would look like that. As it goes around the wire. So this is Biot Savarte for a current carrying wire. It's not easy. And what I mean by that, it's not easy to use it. It's tough. In fact, we're going to take a look at trying to set up what it would take to figure out the magnetic field around the wire. But even right now, just looking at it, every time I pick a different section of wire here, the angle's different because the wire's not straight. My distance to point P is different. So if I looked at this piece right here, I've got X in this direction, and I've got R, in this direction. The only thing that's good is that if you look carefully, no matter which portion of the wire I choose to look at, it always produces a magnetic field that is out of the board at this location. Do you see that has to be true? Now, I want you to think of our time way back. We were first doing electric fields for long wires that had a uniform charge density. Do you remember these problems? They were absolutely no fun. And we might be at a point some distance Z away from those wires. And I'd say, can we figure out what the electric field is from this charged wire that's just sitting in space? And we'd pick a piece of wire and say this wire has charge dq. And the wire is located, some distance r away from my point. And we usually go a little bit further and say that would be a distance x along the wire from the perpendicular distance z. Remember us setting these up? If not, then you probably just, purposely got it out of your head because it was terrible. And we'd say that there'd be a portion of an electric field this way. And the size of that piece of electric field, well, that would be, 1 over 4 pi epsilon naught times dq over r squared. And then we begin the arduous task of trying to add up all of the pieces. And one of the major sticking points was the fact that every single piece, no matter where it was, caused an electric field contribution that was at a different angle. So we always had to look for a symmetry so we could kind of cancel out off-axis components and add together all the components that were in the same direction. You guys remember that? If not, we're going to come back to it because we need to practice this again. It's been a long time, and it was no fun back then. If we reestablish this, but not for a bar or a long line of charge, and we consider instead a current carrying wire, that has, say, current I in it, one advantage, and I use the word advantage very, very, very lightly because there's really not much of an advantage, but one distinction, how about we use that, is that the no matter where we are on this wire, whether we're here or we're here, the magnetic field will be in the same direction here. Every piece of the wire will contribute to a magnetic field in the same direction. So everywhere in this side of the wire, the magnetic field is out of the board. Just like everywhere in this side of the wire, the magnetic field is into the board. So there is at least that I don't have to sit and try and figure out what direction each piece of wire is contributing to the magnetic field. On the other hand, each one is a different distance away, and this angle is different for each piece. So there's still going to be a sign that's going to end up in here. And that's going to still require us dealing with the trig, because it's got a cross product. So although we don't have to scale it for the direction using cosine like we did before, the cross product is going to produce a sign, so it's going to make the math just as difficult. So we're going to take a look at two distinct calculations. We're going to take a look at the magnetic field around a long current carrying wire. But first, we're going to take a look at the magnetic field for a single current loop. And this is the current loop and the long current carrying wire are really the only two things that ever show up when it comes to things that generate magnetic fields. I am going to require that you memorize the current loop and the long current carrying wire. Can't write that over there, out of room. Now, I don't know if you guys understand the symmetry here, but the symmetry should be obvious. For electrostatics, we had the point charge, we had the line of charge, we had the sheet of charge. I suggest we memorize all three of those. And the point charge expanded to be a solid sphere of charge, and it was the same. Remember all of that? We had to do derivations using Gauss's law to be able to figure those out. And we did some other derivations without Gauss's law. Those are more difficult, but we tried them out, and we still did some. But those three things you had to know. And at the end, I had asked you guys to have them memorized. Have memorized the electric field for a point charge. Have memorized the electric field for a long wire of charge. And have memorized the electric field for a sheet. I can't emphasize enough how much more frequently the magnetic field for a current loop and the magnetic field for a long current carrying wire comes up. Twice as often would probably be too little. Maybe 3 times more often on multiple choice and on the FRQs, you will be requested to just know these from memory. And they differ by only a 2 pi. So it's really easy to get them switched because they are so infinitely similar. So today, and I faltered at the beginning of my lesson because I was really struggling with my headache and the beanie conversation, but I really want to nail this portion. I want to talk about how we use Biot Savarte to calculate a magnetic field. Tomorrow, we're going to do 2 calculations for magnetic field. We're going to do the long current carrying wire, and we're going to learn Ampere's law, which turns the long current carrying wire into a single step problem from what tomorrow is going to be a multi-step problem when we do it with Biot Savarte. It's like shadows of Gauss's law. Remember how Gauss's law made the calculation of electric fields much easier for certain situations, like ones that had symmetry? Ampere's law is similar. So we'll start with a current loop. And the reason we're going to start with the current loop is that you can't use Ampere's law on a current loop. The only way to do it is through Biot Savarte. So Biot Savarte, will allow us to calculate the magnetic field directly. So here we go. Biot Savarte begins with the partial magnetic field being equal to, again, it's mu naught over 4 pi. And I'm going to change it just a little bit. It's I dx instead of delta x over r squared cross r hat. All the pieces are there. So let's define our current loop as having a current of I that's passing through the loop in a counterclockwise way. I'm interested in the magnetic field produced at the center of this current loop. Nobody probably will ask why a current loop, since you can't have a current loop like this, right? There'd have to be a battery in there somewhere to generate this current loop. It's because you can take any wire and just by bending it in a loop, create a loop in the wire. And this is how we made our electric motors. Does that make sense? That's why we're talking about loops. Also, is it clear to you that the magnetic field at point P is going to have equal contributions from each piece of wire we select? Because A, they're all the same distance away, and more importantly, they're also adding in the same direction. Right? Use your curl rule to figure out the direction of the magnetic field at the center of this loop and test it for different places around the loop. If you do so, you realize that it's got to be out of the board, no matter where I am in the loop, right? So no matter which portion of this loop I look at, I place my thumb in the direction of the current, I'm getting a magnetic field concentrated at the center that points straight out of the board. Are we okay with that? Now, it's not uniform around this loop, but I get equal contributions at the center of this loop from every piece of wire. Now, so let's figure out how we're going to do the math. I will need to select a piece of wire that I will call D. I guess I'll say dx since I'm using x here. The variable here is used to indicate a piece of length. So this is actually an arc length. I'm going to treat it like an arc length. Am I okay to use x for an arc length, or do I have to use s for an arc length? I can. I don't think it makes a difference to me. I just want to make sure I'm consistent with what you guys have been doing before. So our piece of length that's indicated here is actually the arc length. Now, like any good sum, and we've been doing moments of inertia in mechanics, we need some reference so that we can add up our sum from the first contribution of the sum to the last contribution of the sum. So I'm going to point at this piece, but instead of pointing from point P towards my piece, remember R is drawn from the piece to point P. So I want to say that I'm starting, considering that my point goes from here to here, because this has got to be R. But I'm going to indicate that this is where the first piece of current is. And obviously there are pieces of current everywhere around this loop. Is everything okay with that? All right. Now, ds could be written in terms of the radius of my loop. I could write this as r d theta. And the reason why I'd like to write it like this, and if you don't know where this is from, this is delta x equals delta theta times r. It's the translation from linear motion and angular motion. It's also the equation for an arc length. And we in this class have seen it before, but I want to remind you where it comes from. The whole reason I want to do that, I hope, is obvious. I have to add up every piece of the loop. I think it's easier to add them up from 0 to 2 pi because it feels very circular to me and it helps me understand the nature of how each piece contributes to the magnetic field. The book does it by just saying you're adding up the circumference. I just like this better. It feels more real to me. So I'm going to start assembling my integral by using Biot Savarte for my assembly. So I'll start by putting my constants down. And in this case, we are assuming that the current is a constant everywhere in the loop. So I think it's fair to bring that out and just leave it as I. Bless you. I'm going to replace dx with r d theta. And I'm going to consider my cross product now by looking at the direction of r and the direction of ds, which has to be this way. And note that no matter where I am on the loop, that's going to be the sine of 90 degrees. Agreed? Because the radius is always going to be perpendicular to the current. I'm also going to point out that every single piece is located the same distance away. Now, I know the bell just rung, but all I have to do is draw one more thing and we're done. So I really want to just say, okay, if I want the entire magnetic field, I need to add up over the entire loop, which means starting at angle 0 and ending at angle 2 pi. Does that make sense? Now, if you'll look closely, everything in there is a constant. So you're left with the integral of just d theta. So verify this tonight, that this is the size of a magnetic field generated by a loop of current. It'll be important for our uses tomorrow. Small aside for a moment. If this is point P, just a place in space, and I have a positively charged particle traveling straight towards point P, do you realize there'll be no magnetic field produced at point P? The direction of V and the direction of R produce an angle of 0 degrees. So if the particle's traveling head on, we get no magnetic field if the particle's traveling directly towards you. Electric field, yes, but magnetic field, no. And that's purely because the Q V cross R produces an angle of 0 degrees. And therefore, our magnetic field is going to be 0 for this particle. I didn't bring that up yesterday, and I had meant to, because that's going to show up.